Welcome to a read along with Dr. Powell in the book Discrete Perspectives in Mathematics. This is subsection 4.4.7, Geometric Consequences of Associativity. All right, so let's look at a problem. Let's suppose that we have two green lines and we have some points on one and points on another in order like this, and then we choose to draw some red lines to connect them in a crisscross pattern like this. Then we say, hey, look at those two intersections. Let's draw a line through them. So we draw a line through them. Now, if we were to draw a line through A and T and a line through Q and C, would that also intersect on the green line, or would it be off the line somewhere? That's a question. Actually, associativity of some kind of cubic type addition is what gives it to us. Now, the associativity idea from the intersection proof was kind of nice because it actually will work not just with an elliptic curve, but with cubics if we have some kind of a cubic addition with an anchor. Now, if you have, now if it's not an elliptic curve, then we don't have a tangent idea that every point doesn't have a tangent, which means you can't add a point to itself, which means that if you're dealing with an addition for finding a third intersection, and then finding its then having an anchor and then using the anchor to get a sum, that might not always be well defined. So it's a partially defined addition structure. The nice thing about a cubic is we can use polynomial. If we have 2 points of intersection and we put in the equation of the line and get a polynomial in x and then do polynomial division, we can always get a third intersection, which is kind of nice. And then with an anchor, we can get something going on here. So we actually have something very akin to it. The only problem is maybe tangent lines messing up, or actually getting things really holding with two, with just two happening, or something like that. So we have some issues happening there. So it's only a partially defined addition process if we go to cubic addition. So no way of making that into a group. However, one thing about it, not only it is partial, but it actually is associative. So we can use associativity of cubic additions. In fact, if we have 3 lines, remember, 3 lines is a cubic. So we can actually do an addition process, an associative addition process between points, at least where the addition is defined. It's not defined everywhere between all points, but at least on where it's so it's not a group at all, but it's a partially defined addition process, which happens to be associative as long as we have an anchor to help us out. So we need an anchor, and we need to make sure addition works and where we're choosing. But we know that where we choose it, it's actually associative, and we can use that fact of associativity to prove geometric facts, such as this one. So we want to show that if we draw a line from A to T and C to Q, we also intersect on that green line. So how would we do that? Well, that's an exercise to the reader here, but we can kind of think about it a little bit as well. Okay, let's just kind of look at this. So show that knowing that the line AT, third point of intersection, is the same as showing that the third point of intersection of the line used for A plus B plus C is the same as the third point of the intersection used for that. Okay, and the anchor we're going to use is O. All right, let's take a look at that for just a minute. Okay, so let's take a look at this. If we want to add A plus B plus C, how do we do that? So we have A, we start with A, and we draw a line through A and B. Look at the third intersection point. Then we draw a line through the third intersection point and the anchor. And actually, it's going to be Q. You see why? Because this green line was defined as crossing the intersection of A and B and Q and O. That's just how we drew that green line, right? So we already had this going on right here. Um, so crossing A and B and O and Q actually intersected on that green line. And that intersection was actually the point that we used as the third intersection point and the line that we were drawing between O and that to get Q. So really A plus B is actually Q using O as an anchor. So we could even just write that out just to kind of have that handy. So we know that Q is actually A plus B. So in a similar manner, if we were adding B and C together, B and C, um, so if we were adding B and C together from here to here, um, kind of an analogous argument would actually show that T itself is actually B plus C. All right, so A plus B. All right, and then that one is, and this guy is B plus C. Okay, and let's take A plus B now, and um, let's add C to it. So let's do that. So to add C to it, we take this line. Actually, so this red line is actually the line we want to take. And it crosses the green right here, right? So it crosses the green, so right here. And so that's the point. So that's a point right there that we would like, if this operation is associative, this point should be the exact same as when we draw a line between B plus C and A. That should work. Oh, but it is associative, which means that these two lines actually intersect the green at the same location. So we're done by associativity. Associativity means that we're going to end. So the last line that we draw is going to be the same. Or well, we're gonna make it here because when we take a vertical partner, well, it's not really a vertical partner, but a line through. We draw a line through O, right? We're going to get to this point, but we don't need to go all the way to that point. We can go right before, and that should match up if the two additions are going to be the same. And so since by associativity, them being the same, they're going to match up and we're going to be good. So you can look at that a little bit more, flesh out the details, and see if you can kind of understand what's happening with that. All right. So thank you for watching, and that'll conclude this video and this little subsection.